Right, let's have a look at this then. Here, this integral here, remember we did the 1 minus sine squared is cos squared thing. Can you see in terms of its form, this looks like that if we times by 9 all the way through. See that? And then you can square root this, can't you, to 3 cos theta. We've got the square root around it. So, if you see x squared corresponds to this component here, then the square root of this will be 3 sine theta. So let's put 3 sine theta in, shall we, and see what happens. Let's try that. So try x equals 3 sine theta. We use theta as a symbol when we're dealing with trig customarily. You could use the symbol u, it doesn't matter. So dx du then is equal to 3 cos of dx d theta. Get it right in a minute because we're differentiating with respect to theta. Sine goes to cos, 3 lots of. So I is equal to then, let's see what we get. 1 over, now we've got this square root of 9 minus this squared, and this squared is 3 sine theta times 3 sine theta, which will be 9 sine squared theta, times dx, and dx will be 3 cos theta d theta, won't it? Bring the d theta up. So that's equal to then, remember the formula for this? We just wrote it down a moment ago. Flick back if you need to. That would be 1 over 9 cos squared, because 1 minus sine squared is cos squared, and there's 9 lots of it. 9 cos squared, square rooted is 3 cos theta, times the 3 cos theta above, and now they'll cancel, which is nice. Integral of 1 d theta is equal to theta plus k. So we've done the substitution, we've worked out the integration, worked out the integral. So what is theta? It'll be x over 3. See it, x over 3 will equal sine theta, won't it? And then inverse sines, so it'll be inverse sine of the x over 3 plus k, which is what we wanted to show. Good. Part 2 then, let's have a look at this one. That's the integral of 1 over 9 plus x squared dx. Whenever we get something plus x squared with a 1 on top, it reminds us of, remember sine squared plus cos squared is 1. That's the basis of all this. Well, we also wrote down a variation on that. If we divide by cos, we get cos squared, 1 plus tan squared, or tan squared plus 1, is equal to, divide by cos squared is sec squared. 1 over cos squared can be written as sec squared. So that's the formula, tan squared plus 1. Can you see it? So we could write that as 1 plus tan squared. It's starting to look like it now in terms of its form. But if I put a 9 here, 9 of these, so it's 9 of these, plus 9 of these, of course, equals 9 of those. Now that's now looking like we can make a substitution here, can't we? If we let x equal 3 tan theta. Let's have a look what happens when we do that. Let's just try it and see if something comes out from it, which it should. So try, these are all the same, these ones, in principle. X equals 3 tan theta then, which is what we said. So dx d theta will be 3 tan differentiates to sec squared theta. So we can replace dx by 3 sec squared theta d theta. So let's do that then. I is equal to the integral 1 over 9 plus this squared is 9 tan squared. And then the dx we can replace by 3 sec squared theta. D theta, bring the d theta up. The thing underneath, we just wrote that down, look back if you need to. That was 3 sec squared theta. And on top we've got 3 sec squared theta. So they cancel, we just get left with 1, so it's equal to theta plus k, isn't it? And theta, x over 3, remember, is tan theta, isn't it? So shift tan, x over 3, inverse tan of x over 3, plus k. And that's what we needed to show in part 2. Oh, there's a third somewhere, so I've made a mistake here. Where have I made the mistake? X is equal to 3 tan theta. In the answers, let's have a look then. Okay, so x equals 3 tan theta. So we get 109 plus 9 tan squared theta. And that's equal to 9. Remember 9? It was 9 here, wasn't it? That's the mistake. And then 3 over 9 is a third. That's it. Next one. Part 3. I is equal to the integral of x over 9 plus x squared. This is nice because you've got the something underneath differentiates to a multiple of what we've got on top. So here in these ones we just simply try u equals, like the ones in the previous question, 9 plus x squared du dx will equal 2x, won't it? And then the x dx will be du over 2. And we separate it out. So I equals then x dx is du over 2, so we can put the half there. The du 1 over, and the 9 plus x squared is just u. So this is log u, and it's a half lots of plus k, constant of integration. And that's equal to then a half log of u, which is 9 plus x squared, plus k, there's u, which is what we wanted to show. Part 4. The integral, now this is a definite integral, 1 over the square root of 9 minus x squared dx. Remember, that looks like the very first one we did in form, doesn't it? Remember? 9 minus, remember 1 minus sine squared is cos squared. So 9 minus 9 sine squared will be 9 cos squared. So that looks good. So we'll need x equals 3 sine theta, won't we? So let's try that then, shall we? X equals 3 sine theta should work out okay. And then what do we do? Dx d theta is equal to 3 cosine theta. So we can replace dx. So this is I. 1 over 9 minus x squared. 9 minus this squared is 9 sine squared. So we've got 1 over the square root of 9 minus 9 sine squared. And then the dx is 3 cos theta. And this here is equal to, this is just 1 minus sine squared is cos squared, so it's 9 lots of cos squared, which is 3 cos theta, which will cancel. So it's going to be 3 cos theta on top. This works out 3 cos theta d theta, which is the integral of 1 d theta, which is equal to theta. Now it's between 0 and 3, so when x is 0, then the sine theta must be 0, so theta must be 0, because that's the sine value. Okay, and when x is 3, 3 over 3 is 1, so when is sine theta 1? Was first one when theta is pi over 2, so we can put the upper bound as pi over 2. So it's evaluate theta between pi over 2 and 0. Top value is pi over 2, bottom value is 0. So the answer is pi over 2, which is what we wanted to show.